All right, our first Mental Model Monday. First, before we get into it, let's talk briefly about what Mental Model Monday is all about. Mental models are frameworks, or models, I guess, for understanding the world. And the more models that you kind of have to analyze the world, the 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 easier it is to look at a situation that seems complex and distill it down to its more essential parts. It's easier to identify errors in people's reasoning. It's easier to see structure where there doesn't seem to be structure. And it can just overall help you make better decisions. The more models you have that you can use effectively, the better, more clear you'll be able to think. So I adapted these from a website called Farnham Street, and it's linked in the presentation. But if you just Google Farnham Street, it'll show up. They have, I think, over 100 on the one document that's linked throughout this presentation. So the first mental model we're going to talk about is the map is not the territory. So first, think about a physical map of the state of Michigan, let's say. All right, you open the map, you see all of the cities, you see the roads, and that kind of let's assume it's a road map. You see the roads, you see the cities, you can figure out how far away cities are from each other by road, and that kind of thing. This is pretty clearly an abstraction, right? It's clearly not the territory, which would be the state of Michigan. If for a map to perfectly reflect the reality of the state of Michigan, for it to perfectly reflect the territory of Michigan, it would have to be the size of Michigan. By shrinking it down smaller, we create an abstraction, but in doing so, we delete a lot of the information from the map. And especially, think of sticking with Michigan, we could have a road map, like I mentioned before, but you could also have a topographical map, which would look much different and would sacrifice a lot of road information, but for elevation information. So different maps have different uses in different contexts. So maps are fantastic for this reason, because we don't want to map the size of Michigan, especially if we just want to know what the roads are like, right, and where the roads go. We want a smaller map. We want a map that we can hold, and we want a map that tells us the roads. Or if it's a topographical map, we want a map that shows us the elevation. Okay, but these inherently have limitations. Okay, so we can extend this idea of a map to things that are not just like physical maps, like a map of Michigan. There are different types of maps. So like another type of map might be a mathematical model. So a mathematical model models a situation. You put in certain inputs, and then it computes and gives you outputs. And a mathematical model can be really useful for making predictions or understanding different scientific different situations in science. They're incredibly useful, but they also have limitations. For instance, if you take the Pythagorean theorem, this is if you have a right triangle, then the two legs squared added together, the sum of the two legs length added together, is equal to the third side squared. Okay? This is fantastic, unless you're on a curved surface. So your map is the Pythagorean theorem. It seems like it's going to be seems like a super useful tool, and it is. It works out on flat surfaces. But as soon as you put that triangle on a sphere, let's say, then the Pythagorean theorem breaks down. Okay, so scientific theories are also maps. So like if you think of the theory of relativity, it's fantastic for when distances are large and the scales are very large. But when the scales are very small, the theory of general relativity breaks down, and quantum mechanics becomes the map that you need for very small interactions between particles and that kind of thing. It could also be just a description of interactions or description of reality. I mean, so for instance, like predicting weather is a map, right? We can predict the weather out to a week to 10 days or so, but we can't predict it out to 6 months or a year. So our tools, our maps for predicting the weather have limitations. Okay, and so obviously maps are necessary. They're super useful, and they help us process reality. So we don't need to take in all of the data for all of the terrain of the state of Michigan, right? If we just need the roads, we can just look at the road map, and it's distilled down to the important information. All right. The problem comes in when it's not just an obvious situation like a map of Michigan. So it's when we don't realize what the limits of our map are. We will find maps that we like, and we will try to maximize their uses. So if we have lots of maps, or if we have just a few maps that we really like, that we really understand well, we will try to apply them in certain situations. And sometimes we're going to fail, like the Pythagorean theorem as a simple example. If we try and apply that in a situation where maybe you're turning something on a lathe or something, maybe your distances are not going to work out right. So we have to have a diverse set of maps so that we can understand a diverse set of situations in reality. Okay. So here's some of the problems that you can run into with a map. And remember, we're thinking map in the general sense, not the just map of Michigan sense. Any kind of tool abstraction that's designed to help you understand more complex processes or more complex situations in the world, okay? So the map could be incorrect without us really realizing it. This happens, I think, happens quite frequently in like sociology or anthropology, or situations in which we're trying to model complex human interactions. Okay, so we could have something wrong in our analysis and we might not know it. Okay, some information gets deleted to reduce the territory to the actual map, and this is it's a feature, right? This is what we want, but it can also be a problem because that information that gets deleted might be useful. So, for instance, when we create a roadmap at one point in time, and then there's road construction and an intersection changes or something, and that's not reflected in that map that was created, that's a problem. There's information there that we don't have. Okay. A map requires interpretation. So a mathematical model, a sociological model, a scientific model, these all require interpretation. And because it requires interpretation, it opens up space for people to screw it up, right? To make a mistake in the interpretation of the model. It opens the door for bias, right? People that have certain axes to grind or certain slants in one direction or the other, they can interpret the model in certain ways that fit their narrative or fit the way that they're trying to skew the information. Think about this. Think about a model that's built on history. So lots of models are like this. To take it, just floods, for instance. So the history of floods in in whatever county you live in. Okay. You may have heard of things like a 100-year flood or a 50-year flood. Well, the worst flood in history like of may not be the worst flood that will ever happen, right? So the worst case is built on the worst case is built on the worst case in history, and it's possible that the actual worst case situation is yet to come. Okay, so there's limitations in models and maps that are built on history. Not that they aren't useful, but just that we have to understand their limitations. And then this is a good concept to understand. The further the map gets from physical reality, the harder it gets to see its limitations. So if we think about like the mathematical map, right, the Pythagorean theorem, we say flat surface, right triangle. We put in all the what would you say, the definitions at the beginning, at the outset, and we say if we have these things, then the Pythagorean theorem is true. There's no way out of that. Right? That's a mathematical fact about the nature of the world given those definitions. Now, the further you get away from that abstract concept of the Pythagorean theorem, then you get to, let's say, scientific theory. So like the theory of relativity, it's a little bit further away from just those axioms or those definitions that we have in just pure mathematics. That map works very well in certain contexts, but not in others. But it's fantastic in the context for which it was designed, right? If we get more abstract, so we get to like the societal level, or like the situation we're in right now, where we're trying to predict how this disease is going to spread throughout society, it gets harder and harder to see its limitations, and the map is going to have more limitations the more complex the situation is. So you just want to keep that in mind as well when you're thinking about this. Okay. Wrap it up here. The first step to overcoming the problems is to recognize that a model has limitations, even some you may not be aware of. So think about, if you want to be able to kind of stand outside of yourself a little bit and understand, like, okay, I'm using this model to interpret the world, and I understand that it's going to have limitations. So I need to keep my eye out for those limitations, right? And this is the last, to kind of end this one. When the territory and the map differ, follow the territory. So if all of your experience is telling you that your map is wrong. Take the simple example. You're driving in a car and you have a map and the roads don't make sense compared to the map. Then you should follow the territory, right? I mean, you've got a bad map on your hands. So you should either find a different one, change it, or just follow the territory wherever you need to go. And this is also going to be metaphorical, right? So when the territory and the map differ, you want to follow the territory. If you have any questions about this lesson or anything, then shoot me a message, or we'll chat in the next Zoom call, and you can bring it up then. But otherwise, that's the first Mental Model Monday.